Okay, so I'm Kajal Khan from Ansys India office. I'm a senior application engineer working mainly focusing on the structural and electronics reliability side. Today I'm going to talk about this topic called electronics reliability using Ansys Sherlock. So I'll start with a quick overview of the Ansys Sherlock. So this slide shows the typical design process for a reliability electronics product. So before going into the electronics reliability, if we define the reliability, so it's the probability that a product will perform its desired function for a specified period of time without any failure in the function. So traditionally, how we meet the electronics reliability is by using this cycle called fix, design, build, test, and break workflow, where we first design the product and then build it, and build the prototypes, test the prototypes, and if it breaks, then we fix that and repeat the entire loop. And it is not only time consuming, but also costly because it involves a lot of effort and money. Now, if you can replace some of the physical process involved over here using computational model, then you're going to save a lot of time and money. That's where Sherlock comes into the picture. So, and this Sherlock can be used to reduce the number of design iterations in this entire cycle, and it can reduce the eventually it can reduce the amount of time that you are going to invest in this entire process. Now, when we talks about the electronics reliability, we actually deal with some of the failure mechanisms that we typically see in the electronics industry. And if we list out these mechanisms, so these are mainly caused by the thermal issues, vibration issues, or some kind of humidity and dust environment. Now in Sherlock, we are specifically focusing on these two aspects, that is the thermal and vibration aspect, which causes majority of the failures in electronics. And in the thermal and vibration, it is mainly caused either by fatigue, which is high cycle fatigue or low cycle fatigue, or it could be like a shock or drop test, or bending over stress because of the bending. So in Sherlock, we're going to deal with all these kind of failure mechanisms and understand how your product is going to sustain over time. So what is Sherlock? So Sherlock is a ADA tool, that is automated design analysis tool, that is based on physics, which is not based on some design rules or some past data, but it is based on physics that can provide fast and accurate live predictions in the component level or board level as well as the system level. And how it does all these things is by some powerful pre and post processor. So when I talk about the preprocessor, it is basically the conversion of the ECAD that you get from your PCB design tool. So the preprocessor, what it does is that it converts that ECAD into a 3D MCAD or mechanical CAD that you can use for your reliability or failure analysis. So Sherlock can generate this kind of MCAD in just few minutes and with just few clicks of your mouse button. Uh, Another thing is that Sherlock has a powerful post processor which not only predicts the temperature, stress, and strain in your system, but also but also tells you that how much heat is too much or how much stress or strain in your system is too much strain to cause any failure in the system. Now coming to the Sherlock GUI, so the workflow starts with importing the ECAD file. It could be ODE++ or IPC2581, or it could be some other files like Gerber. Followed by, so we have a lot of libraries inside Sherlock that converts your ECAD into MCAD. So we update the ECAD and the part list inside the ECAD. So we update it from the libraries. Finally, we define some loading environment. It could be thermal environment, a shock, or vibration environment. So we define the thermal environment and model the system or model the PCB and solve it. And at the end, we get some life prediction or reliability curve, like how long or how many years this product is going to sustain without any failure. So that's the whole objective and the workflow in Sherlock GUI. Coming back to the individual steps, so we start with the ECAD. As I mentioned, it could be like ODE++ or IPC2581 or Gerber, and we read all these files seamlessly. And we define the duty cycle in terms of the thermal environment or vibration environment. it could be SOC or drop. So we define these environments, and with the help of these libraries, we convert the ECAD into a mechanical CAD. Now, this Sherlock has these inbuilt libraries, like the part library. We have around 600,000 of electronics components that are already integrated inside Sherlock. So whenever you bring any ECAD or electronics CAD, it reads which component is this, and then based on that, it updates all the properties of that component, like the dimensions, material properties, and things like that. Similarly, it has thousands of packages inside. It has several hundreds of electronics materials, which is specified to specific to suppliers and electronics products. We have several hundreds of laminates library, which makes the PCB layers. And we have the typical solder library, which could be like lead-free solder or leaded solder. So with the help of these libraries, we can convert the electronics CAD to a mechanical CAD in just a few clicks and within a few minutes. So that is the unique point in Sherlock for using the tool. Now, once you convert it to a mechanical CAD model, then the remaining things, like you have to model it and generate the finite element mesh and solve it to get the results. And the results could be in different. You can see the results in different ways. It could be a tabular results, like frequency results, or it could be showing the mode shapes. It could be like the contour plots of strain or displacements. And it also gives the Y-wheel plot of individual failure mechanisms, as well as the combined risk of the entire PCB following all the failure mechanisms, which could be like thermal environment or vibration environment or shock, or it could be any other things. Also, it lists out all the components and gives a color coding whether the component will pass or fail within the given time period, and within the given environment, loading environment, so that the component is going to pass or fail. That kind of color coding it will also provide. So the results you'll get in different forms, and these are very intuitive and easy to understand. Coming to the different analysis that you can do inside Sherlock, so you can do thermomechanical analysis, you can do natural frequency or modal analysis, you can do harmonic vibration analysis, also you can do random vibration, mechanical shock or drop. A very important analysis, that is solder fatigue, which is very typical to semiconductor industries, and then you can also do the through hole fatigue inside the through holes in PCBs, and also you can do like the in-circuit testing analysis. So these are some of the analysis that you can do. I have not listed all the things, but there are many other things that you can do. Now, coming to a case study, so this study shows how you can effectively use the tool for different design scenarios that you encounter in your day-to-day life. So, for example, if you're a designer and you are going to place this infotainment module inside your PCB, you need to identify at which location you should place this component, whether you place it at the bottom or at the center or at the top. So as a designer, your job is to understand or decide where to place this component. So and the loading environment is, you have a mechanical shock, and it should sustain 30G shock for 50,000 times. So that is the design scenario, and if and you have to understand where to place this on the IC, that is the system SoC component, and to reduce the chances of failure for this kind of loading. So within Sherlock, you can just bring the PCB and this component, and you can just give a quick run to understand how this placement is working in terms of the reliability. For example, if you place this component at the center, you end up with very less life. So if your desired life is 10 years, you are ending up with around 3 years for 20% probability of failure. Even if you see it is failing, it is having a probability of failure of 5% within like less than 2 years. So this is not going to sustain this. If you place it at the center, your component is not going to sustain for 10 years. So you have to make some design decisions to improve the reliability of this component. Naturally, one choice could be like place this component away from this hotspot that you can see over here. So if you just switch the location from the center towards the left side, you see uh, as soon as you change the component location, your life is increased to more than 9 years. So you're almost close to your design requirement. So you can do these kind of design iterations within a minute with just a few clicks. And it gives eventually tells you like how the components behave in terms of reliability. Also, you can put some mounting conditions or mount points inside the PCB just to reduce the amount of strain or hotspot, and so that you end up with a very much higher life as compared to the baseline design. Not only that, you can have other design scenarios, like you can add an underfill under this IC, and you will end up with much higher life. So this component will not fail if you add on underfill inside the IC. So that kind of design changes you can make within just a few minutes, just a few clicks. Now coming to some of the customer success stories that we have in the past couple of years. So this is one example from an American auto manufacturer. So they could get a ROI of more than 40 because they eliminated a lot of thermal cycling test using the Sherlock software, which they used to do using physical testing. Similarly, this is an example of a global SSD manufacturer. So they manufacture the storage devices, and they do they design a lot of PCBs annually. So around 10 PCB they design annually, and for each PCB they have to design reviews. So eventually they could eliminate around 20 designs, 20 testing scenarios, and they could reduce the time to market by more than 6 months. It saved more than 7 millions in terms of test cost for this SSD manufacturer. It shows some of the testimonials from the customers, so you can see that people our customers are appreciating our effort in the tool.